Okay, in this video, we are going to look at a force to frequency circuit. And that's the circuit I have built on my breadboard. And I'm going to be using an FSR, a force sensing resistor. That's this device here. So as I apply pressure to my FSR, I'll get a pulse train coming out of my circuitry. And the harder I press on my FSR, the higher the frequency of the pulse train. So we could feed that pulse train into a microcontroller and measure the period of the pulse train and actually determine the pressure applied to the FSR. Now normally we use a voltage divider circuit with the FSR and we feed the output into an ADC converter of a microcontroller. But this is just another way of doing it. We're using a frequency instead of a voltage. Now if you're not familiar with FSRs, we'll go through a little refresher. Now a change in force applied to the device will cause a change in resistance across the two output terminals. Now they're not as accurate or precise as a strain gauge or load cell, so I just use them for general purpose pressure sensing. Now when no pressure is applied, they look open circuit to an ohmmeter, and if you apply pressure to the device, the resistance will drop until the device becomes saturated, which is around 1 kilo. So any more pressure will not cause any change in resistance. Okay, I have my FSR connected to my Arduino Nano. So basically I have a voltage divider comprised of a fixed 47 k ohm resistor and the resistance of the FSR. And I have that fed into one of the channels of the analog to digital converter on the Nano, A0. So if I press on the FSR, I can cause the first LED to come on. And if I press harder, the second one, third, and fourth. So the harder I press, the more LEDs I could turn on. As you can see there. I could tell that it's very sensitive to turn the first one on. And then as I go to the second and third one, I have to press harder and harder. I could feel that non-linear curve. Okay, that's one way to interface an FSR using a voltage divider and feeding it into a microcontroller ADC. But in this case, we're going to use a little oscillator using a CD4093 Schmidt trigger NAND gate. It's configured as an RC oscillator. So the R and the C determine the frequency output of the little oscillator. So this is our C, that's our capacitor, and the FSR will be the resistor. So by changing the value of the resistor as I apply pressure, it's going to change the output frequency of the oscillator. So instead of hooking it up to a scope, I'll hook it up to a speaker. So I'll turn on the speaker. I have that hooked up to the output of the oscillator. So if I press on the FSR, see I get a low frequency oscillation. Now if I press harder, now I have a little filter, this little capacitor here, it changes the dynamic range. If I pull it out, now you'll see the frequency won't go as high. So now we can play around with the dynamic range of the circuit. I put the capacitor back in. So it's a lot more sensitive and it goes to a higher range. Okay, here's the schematic diagram of my pressure to frequency circuit that I built on my breadboard. Now I'm using two of the Schmidt trigger NAND gates from the CD4093, and I've connected the inputs together so they're configured as inverters. Now the first inverter is the RC oscillator. It's an astable RC oscillator, and the second inverter is just a buffer that's buffering the first stage. Now the R of the RC oscillator is the FSR in series with the 56K resistor, and the C is the 0.1 microfarad capacitor. And the R and the C determine the output frequency of the oscillator. Now as I put pressure on the FSR, the resistance will drop, and the output frequency will increase. Now the 0.47 microfarad capacitor is my component that could change the dynamic range of the circuit. So it's actually a little bypass capacitor. You can think of it as a frequency-dependent resistor, so as the frequency goes up, it's going to bypass more, so it'll charge up the capacitor faster. So we'll get a higher dynamic range, we'll actually get a higher frequency output. Now when the FSR is not being pressed, when it's idle, it's pretty well open circuit, so the oscillator won't oscillate at all because there's no way to charge up the capacitor. So either the output will be either a steady high or a steady low, depending on the condition of this capacitor, if it's charged or discharged. Okay, I did a waveform capture on the output of my pressure to frequency circuit. And you can see this is the leading edge of my press and release. So you can see the first pulse is not as hard because I'm just starting to press down on the FSR. And as I press down, you can see the periods get smaller. indicates more pressure. And you can see there it's getting smaller and smaller as I'm pressing. And if we go all the way to the end of the press and release, so there's the middle, you can see that if I zoom in, there's nice clean square waves. And if we go to the very end, on the release, you can see the pressure being released on the release. This is the very end of the press and release. So that's a signature of the FSR, a press and release, which you could actually input into a microcontroller, and you could extract the signature information. Okay, now you know how this circuit works, so you could be creative and come up with your own ideas how to implement an FSR in your project. So in this case, we could build an impact detector with an impact signature, and we could feed that into a timer counter of a microcontroller. And because the timer counter is independent of the CPU, it creates simpler code. And you could also use an FSR as a feeler gauge, so you can measure the interference between two parts of a machine, and it'll give you an output. Or you could have an audible impact detector, or a variable clock frequency feeding digital logic, and as you press harder you'll get a higher clock frequency, so it'll become like a speed control. So come up with your own ideas how you can interface your FSR to your project. Okay, using the same technology, you can obtain a flex sensor like the one here. Now instead of applying pressure to the sensor, we flex the sensor, and as we flex it, the output resistance will change. Now there's other devices. There's one device called E-tape. It's a precision sensor, and it will measure the level of a tank, either a liquid or dry substance that flow like salt or sugar, and it will actually give you the level of the tank. So in this case we have a flex sensor. You can see we could use the same circuit and feed that into a microcontroller, and we could actually get flex angles. So I hope this video gave you some ideas how you could build your own devices using an FSR in your project.